This is a presentation for our Team 6 project for biomedical equipment design for low resource settings organized by Engineering World Health. This has been a collaboration between Engineering World Health facilitators, that was Mercy, UC Berkeley students, for our team, that's Sarah Abu Bakr, myself, Umair Alam, and Isabel Pomil, and University of Nairobi students for our project again, that's Josefa Munawar and Sebastian Knowledge. The task of this project was to come up with a solution to a need faced by hospitals in low resource settings. The project that we decided to embark on was to devise an affordable method to measure oxygen concentration. Before I jump into the details of the problem as well as the solutions, I just want to go through the table of contents for this presentation. So we'll start with the problem, the existing solutions to that problem, the solution that our team came up with, the details of that solution, including technical feasibility, the next steps for this project if we were to take it to market, for instance, and then finally a conclusion for the project. Having an affordable method to measure oxygen concentration is vital for oxygen concentrators that are used in hospitals. An oxygen concentrator is a medical device used to deliver oxygen to patients. It pulls in air from the surroundings, compresses the air, removes nitrogen and other impurities from the air via filters and sieve beds, and delivers the purified oxygen to the user via a mask. Oxygen concentrators are a popular choice to use for oxygen therapy in hospital settings because they're portable, and when working with the expected efficiency can produce air with 90 to 95% oxygen purity. Additionally, these devices don't need large infrastructural setups like those required for piped oxygen supply, and are also not as unsafe as oxygen cylinders. That being said, there are challenges when using these devices in low resource settings. For example, sometimes the devices coming in might be close to end of life because these devices aren't brand new and instead have been donated from some cause. Also, because of regular mechanical wear and tear, these devices might not be running as efficiently as expected. All of this can lead to the devices providing less than the desired 90 to 95% oxygen concentration. Another factor in this degradation could be dust, dirt, and debris. So, it is essential that there should be devices that can monitor the performance of an oxygen concentrator and give us a reading for what the oxygen concentration is.
Looking at existing solutions to measure oxygen concentration, the primary option is an oxygen analyzer. These devices assess the performance of oxygen concentrator systems through oxygen concentration, oxygen purity, and flow rate measurements. Some of the drawbacks of these devices include a lack of an alarm system that alerts doctors and other providers when the oxygen concentration dips below a certain percentage. In addition, they tend to be poorly accessible, being separate from oxygen concentrator devices and generally expensive, ranging between $200 and $700. Finally, they're also not available to places that lack electricity, generally requiring a solid power grid that is reliable in order to be used in hospitals. So, what is our solution? As a team, we came up with an oxygen analyzer that offers continuous oxygen concentration analysis with an off-the-grid power source at an affordable cost. Looking at our diagram, our oxygen analyzer is connected directly to the oxygen concentrator. This concentrator then feeds into a humidifier bottle, and finally, using T-shaped tubing, is inserted into our oxygen analyzer. Our analyzer uses the standard 5mm inner diameter, 7mm outer diameter tubing and allows it to be more universal, working with multiple oxygen concentrator systems. Looking at our analyzer specifically, you can see the alarm or LED, the O2 concentration and battery percentage on a small screen, and on the back we have a battery access panel for allowing it to run without an electric grid. Finally, oxygen leaves our system and then it's delivered directly into a patient.
In more technical terms, our device utilizes an ultrasonic oxygen sensor, which is an accurate, reliable, and also common method of oxygen concentration measurement among different analyzers. And the way this specifically works is the ultrasonic wave propagation speed changes upon gas composition, which allows for the concentration to be measured. And this ensures that our device will still function properly, since the method for the measurement is not an abstract design, but it's the other device functions which differentiates it from other products. And specifically, this includes our analyzer being designed for continuous use, meaning it's constantly reading and displaying oxygen concentration rather than taking individual measurements, as well as its alarm. And next, our analyzer is connected to the humidifier of the concentrator with PVC tubing, and it feeds the oxygen gas from the humidifier to the analyzer and the patient via a T-shaped tube connector. We also decided to go with a 14-volt lithium rechargeable battery, which provides long battery life, and it also deems constant power supply unnecessary, which is useful for low resource settings. And finally, as described by Isabel, the LCD display will show the oxygen concentration and battery status, and the alarm with a red LED will flash and beep when the oxygen concentration drops below 95% in order to notify the user. And here we included a more eye-friendly graphic to identify our product's features, listing their functions which were previously described. And in terms of the cost, the estimated overall cost of our product would be around $200. And this is an estimate for the prototype and single production based on the sum cost of different parts of the device. However, over time, a higher production rate would cause for reduction in cost. And already at $200, though, this price is cheaper than traditional analyzers when it also implements new features.
To gauge the technical feasibility of our oxygen analyzer for use in low resource settings, a survey was carried out using Google Forms. And from the responses that were recorded, one of the issues that came to light was the accessibility of the oxygen analyzers. Around 86% of the respondents deemed the current analyzers to be highly inaccessible, mainly because of how costly they are. Depending on the manufacturer, the cost of an analyzer could go beyond $700, which cannot be possibly afforded by underfunded healthcare centers. Another issue that low resource areas face are the blackouts, which from the results we can see is a fairly common occurrence. For healthcare centers that are located in such areas, oxygen concentration monitoring becomes a challenge if the device in use is entirely dependent on the grid power supply. For these reasons, our oxygen analyzer has been highly preferred by the respondents that took part in the survey, which makes it eligible for use in low resource areas, mainly because of its affordability and because of its long-lasting rechargeable battery pack.
On to the next steps, we are working on creating prototypes, which will involve developing details, designs, and determining material required. Then we need to have a comparative testing to determine the usability, error handling, and functionality of our concept solution. On things that we need to improve are feedback and impression design and impression design. On implementation, we should work on purpose, scope, user interface, and key functionality and funding opportunities. Thank you.